Good morning, everyone. Today I'd like to share with you some of my PhD work where here at Queen's and in collaboration with the Australian Antarctic Division, where we looked at the use of geosynthetics in Antarctica. And if there's one or two main things that I want you to take from this presentation, first, it's that even in the cold and harsh climate of Antarctica, geosynthetics are an appropriate and tool that performs well. And the second is that by improving construction techniques and tailoring the techniques to this environment, we can improve the performance of these materials in this harsh climate. So this project takes place at Casey Station in Antarctica. Casey Station is an Australian Antarctic research station located approximately 4,000 kilometers south of Perth, and it's operational year-round. And one of the realities of a year-round operational remote station such as this is that you have to generate all your power on site. Casey generates all its power using diesel generators, and it stores about 1 million liters of fuel on site every year. And one of the realities of storing this much fuel is that fuel spills are a reality. And Casey Station has had several fuel spills in the past, with the most recent being about 3 years ago. So it's very important to minimize our human effects of these fuel spills on the environment. And one of the ways we do that is through the use of geosynthetics. And that is where we come in. So my research looks at geosynthetics for barrier systems in Antarctica. And I'm going to be talking about 3 types of geosynthetics: geomembranes, geotextiles, and geosynthetic clay liners, or GCLs. And geomembranes are polymer sheets that are usually 0.5 to 2.5 millimeters thick that are used to prevent contaminant migration. Geotextiles are fabrics that have numerous geotechnical functions, and geosynthetic clay liners, which are the focus of this talk, or GCLs as I will be referring to them, are multi-layered fabrics impregnated with bentonite, which is a high swelling clay. We use these materials for a composite barrier system for our biopiles. And the biopiles are contaminated soil that's contained by a geomembrane placed on top of a GCL. You might be wondering, why are we even using geosynthetics in Antarctica? Isn't there a material there that we can use? Well, there's no clay available to construct a liner, and we can't just take soil off-site because you can't remove anything from the continent. So we have to remediate on site. And while we do that, we have to prevent any further contamination. So I had 2 field seasons at Casey Station. And during those 2 field seasons, I had 4 project objectives. And the first was to remove the source contamination from the most recent fuel spill. The second was to decommission one of the existing biopiles. The third was to build and monitor a test plot to look at GCL hydration. And the fourth was to build a new biopile using everything we learned. So the first task was to remove contaminated soil from the existing fuel spill. This was a 6,000 liter fuel spill that occurred right before I got there, and it impacted this building footprint. And this was a critical path item because a building needed to be built in this location by the end of the season. So we had to remove all the contaminated material and regrade the site so that construction could begin. And you can see that there's a significant amount of material removed from this site. The top of the pink drum is where the original ground surface was, and I'm standing there in the blue. And you can see that we removed material up until about my waist height. So in this pit, we had air concentrations of 200 ppm volatile organic compounds, and any groundwater had free-phase diesel in it, so it was extremely contaminated. And we had to fill this pit back up with something. And this is where task 2 came in. We used material from this existing biopile to regrade the site. And this biopile was built in 2010 and decommissioned in 2018. And this was the first time remediated soil was reused in Antarctica. And it was a full circle moment for this project. While we were decommissioning the biopile, we noticed several things, but one was the condition of our GCLs. we noticed that our GCLs were overlying these sharp and jagged rocks. And this is due to migration of fine material that happens during the melt season. And we can say that this is definitely not the recommended subgrade for these materials, because it can cause damage to not only our GCL, but our geomembrane above. And we can see that it's caused these little indentations or large indentations of our geomembrane above our GCL. And over time, these indentations can become holes. So these are holes from another site in Antarctica, another test plot in Antarctica, and we can see that the holes in our GCL and our geomembrane are over 4 centimeters long. After we decommissioned the biopile, we sent the samples back to Queen's. And at Queen's, I looked at the moisture content, hydraulic conductivity, and the swell index of our specimens. And where applicable, I compared it to virgin numbers. And one thing that really stuck out to me was the variability of moisture content of our samples. So we had desiccated samples with a moisture content of 20% and hydrated samples with a moisture content of 191%. And keep in mind, this is a fairly small site. The biopile site is less than 50 meters by 20 meters. So it's an extremely variable range of hydration for a relatively small area. We also looked at the hydraulic conductivity, and when compared to a virgin value of 1.5 times 10 to the negative 11 meters per second, the highest hydraulic conductivity was 5.2 times 10 to the negative 11 meters per second, and that was for our desiccated specimen. Even though it's an increase, it's still a relatively good number, meaning that this GCL, it would probably perform well in the field. And our swell index test showed that our desiccated samples had a lower swell index than our virgin and our well-hydrated samples. But overall, these are still very good numbers for these materials. This led us to build and monitor our test plot. We know that GCLs need proper hydration in order to perform well. And this is difficult to achieve in Antarctica due to the fact that not only is it below freezing most of the year, but Antarctica is a desert. And we know that the quality of subgrade has a large effect on our GCL hydration. So what have we seen that's happening to prompt our test plot? Well, we saw several variable hydration conditions. And the first is unhydrated material. So even after 2 to 3 years in situ, we saw powdered bentonite when we exhumed the specimens. We saw well-hydrated specimens, which is what we want to see, desiccated specimens like we saw in our decommissioned biopile, and frozen specimens where the GCL hydrated and froze in situ. So our test plot was designed to mimic a biopile where we had cover soil, a geomembrane, and a GCL overlying 4 different subgrades. And the first subgrade was the natural soil at Casey, and this is what existing biopiles have been built on. The second was a sieved soil where rocks and stones greater than 6 centimeters were removed. The third was a sieved soil with a geotextile separation layer, and the fourth was a sieved soil with a geomembrane separation layer. And I just want to show you the difference between our sieved soil and our natural soil. So here we have a grain size analysis curve with percent passing on the y-axis and size in millimeters on the x-axis. And we can see that our sieved soil in yellow has a greater sand fraction than the natural soil in green. And it's over double the sand fraction than our natural soil. But what does this look like? Well, we can see that our natural soil has those large rocks that we saw in our decommissioned biopile 2, but our sieved soil, we remove them and the soil is more uniformly graded. So during the course of the season, we exhumed our test plot and took measurements of our thickness, the mass, took pictures over the course of the season, and we did something that's really, really special. We took X-ray specimens in the doctor's surgery. So here we have the X-ray specimens of our GCL overlying our natural subgrade and the GCL overlying the sieved subgrade plus the geotextile. And if you're not familiar with GCL X-rays, the light portions indicate thicker and better hydrated bentonite, while the black portions indicate an absence of bentonite, either due to an indentation or desiccation cracking. And I really want to focus in on these two boxes over the course of the season. So we have our sieved subgrade with the geotextile separator on the top, and we have our natural subgrade on the bottom. And we have x-rays from 3 dates. December 28th, which is the beginning of the season, January 11th, which is the middle of the season and corresponds to a period of high melt, and February 2nd, which is the end of the season. And let's just up the contrast a little bit. And I want to point out that there's these black lines all over the place. So that's desiccation cracking. And I also want to point out these dark circles in our natural subgrade. Those are indentations caused by those large rocks and stones that are not present in our sieved subgrade. And we can see in our natural subgrade that it's pretty constant throughout the season. There's not much change visible to the naked eye. But with our sieved subgrade, we can see that it starts out desiccated, and then on January 11th, we see those desiccation cracks, the black lines, start to blur. This means that the GCL is hydrating and those desiccation cracks are self-healing. And then they start to reappear at the February 2nd sampling. And this corresponds to the moisture contents that we took throughout the season, where the natural subgrade had a lower initial moisture content that did not change significantly throughout the season. But the sieved subgrade had a higher initial moisture content that increased almost 20% in the January 11th sampling and then decreased again towards the end of the season. All of this led to our task 4, which was to build the new biopile. And one of my main concerns was the subgrade preparation, where we made sure that a mechanically sieved subgrade was placed on a geotextile separation layer. And this was to achieve better hydration like we saw in the test plot and to prevent the migration of fine material that we saw in the decommissioned biopile. From this research, we were able to draw several conclusions. The first is that geosynthetics are an essential component of soil remediation in Antarctica. And the GCL subgrade experienced migration of fines, resulting in deformations in our GCL and geomembrane. But even though this was a non-ideal subgrade that led to variable hydration conditions, the performance properties of the GCL were not significantly affected. We saw that the subgrade had a noticeable effect on our hydration and dehydration of our GCL, and that we were able to track the hydration and desiccation through X-ray imaging throughout the season. We then used recommendations and put forward the recommendations to use a geotextile separation layer and a sieved subgrade in the next biopile build, and this was implemented in 2017. And we can see that geosynthetics are an appropriate solution for environmental protection in this extremely challenging environment. And the methods and strategies for site remediation used here are applicable to other Antarctic sites. Australia is leading the way in this, and I think it's also applicable to other remote sites. And I think this is extremely important, especially as resource expansion moves to places that were once not feasible. I'd like to thank Dr. Lloyd Fletcher and the AAD Polar Medicine Unit, as well as the Australian Antarctic Science Grant that funds this research. And I want to end off with a quote from the second person to reach the South Pole, Robert Falcon Scott. I have come to the conclusion that life in the Antarctic can be very pleasant. Thank you.